understand what the decision boundary is, how we can declare this decision boundary mathematically. Then with that understanding, we'll talk about the linear classifier and how it outputs generate predictions. We'll talk about the concept of a linear separability. We'll also talk about error function for this specific perceptron algorithm. And then we'll actually talk about how we can tune the perceptron's parameters using its learning algorithm. And then with this understanding of a simple linear classifier, we can go ahead and try to turn classification into an optimization problem. We'll talk about some limitation of the perceptron algorithm we've previously introduced. We also talk about why we need a sort of a thick decision boundaries. And then from there, we'll talk about loss regularization and the objective function to turn the entire classification problem into a optimization problem, which can be whacked with your gradient descent. And then we'll briefly touch on hyperparameter selection. Okay, so I will just go ahead and start from the perceptron. So as per usual, let's do some plots. Draw axes. This line is not straight. No. Mm. 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 Okay. So usually we have x and y plot. Wait, let me just copy this axis. So usually we have some x and y plot. And usually we have some random data points. This time I'm going to color code it, so it's like two different classes. Okay, it can be like this. Say something like, okay, not here. Something like this, right? So you have data points from two different classes. And for a linear regression problem, we try to sort of associate the relationship between the x and its output y by drawing straight line. And for linear classification, instead, we are more concerned with how we can draw a decision boundary that is going to separate our two classes. And in this case, the decision boundary, because it's linear classification, is going to be a linear line. And in this case, you can see that one such decision boundary that can separate the two classes will be one that's true the origin, right? So this line perfectly separates the different classes, and this is your decision boundary. Because in linear classification, we're less concerned with how to model the relationship between x and y. Instead of plotting x and y, we'll call this x1 and x2. They're the two coordinates of the point. And instead, our labels will actually be the class of each of these points. So in this case, we'll call this maybe positive class, and this will be a negative class. So your y labels will be different from linear regression. And we can express this set of training set again mathematically. So this is the same expression that you've seen for linear regression. So for I from 1 to n, but the data sets itself, the xi and yi will be declared slightly differently. For your yi, it's strictly a set of 1 or negative 1 in this case. So yeah, 1, you can interpret this as 1 is one class and negative 1 is another class, or 1 is one class and negative 1 is just not that class. And the xi will be slightly different as well. So in this case, because we're plotting on a 2D plane, our xi is actually two-dimensional, right? But in general, xi will be any-dimensional. So actually the notation here should be this, and it should be this. Okay. So with that briefly declared, we can actually go on and talk about how we will actually mathematically represent this decision boundary. Okay, and for in this case where the decision boundary is going through the origin, it can be defined as simply your data points multiplied by the weight equals 0. Okay, so this, you should be familiar with this because Alice has gone through the introduction to vectors, right? And this can be represented as like a normal line to the decision boundary, that is in this case through the origin, and this is orthogonal to your decision boundary, and you realize that for this equation to be true, then x has to be any point on the decision boundary. So any point on the decision boundary will be orthogonal to this normal vector, which will cause this operation to become 0. And with this, we can actually go ahead and define how we get the signs on these classes, right? I said this is positive and this negative. And we'll briefly analyze why on the same side as the normal vector, your points are positive and why on the other side is negative. So if you take one of these points here and we draw its vector representation, which is a line connecting the dot to the origin, okay, like this, and you'll realize that this makes a certain angle. Let's use this certain angle theta with a certain angle t with the normal vector theta, and you realize that for the case where the data points on the same side as the normal vector, t is actually less than 90 degrees. And if we express this expression again as the norm of x multiplied by the norm of theta and cosine t, we will realize that this expression will be a positive if your t is actually smaller than 90 degrees. On the other hand, if we draw a normal, we draw the representation of, let's say, this point here, and you realize that the angle it makes, is the second t, is actually larger than 90 degrees. And this will cause this equation to become negative. All right, so this is why these points on the opposite side of the decision boundary will be negatively labeled. And with this understanding, we can go ahead and declare a classifier. This time will be a pretty basic classifier that can only output a decision boundary that is through the origin. So we call this h, and it operates on x. It has certain parameters theta, and the output of this function is actually just the sign of x dot theta, right? So that will give us the correct label for either side. And again, one thing we have to stress, because the x and they are vectors, and they are of the same dimensionality. So if your xi is say 1, 2, then your theta will also have the same dimensionality as your coordinates. Okay, so that is a really basic classifier that can only produce decision boundary that's through the origin. And you realize that this is pretty constrained, right? So for example, if you look at a new set of data points, this, and you realize that any decision boundary that you draw through the origin uh, might not be able to successfully separate these 2 points, right? So you can draw however you want, it's going to make some mistakes. So the most obvious solutions to this is actually a decision boundary that's somewhere up here, that's offsetted from the origin. Okay, so that's why using a simple case where the decision boundary that crosses the origin is actually pretty constrained for us to classify data sets, right? So we have to find out how we can declare this. Again, this has a normal vector, positive and negative. So let's try to sort of find an expression that can help us declare this. And for this generalized boundary, it's actually a really similar form again with the previous simplified decision boundary. Your data point dot the weight plus a certain offset equals to 0. And you realize that this expression can be slightly rearranged to some form, to a form that you guys might be more familiar with, which is x dot theta equals to a certain constant, and your theta again is your normal vector. And you will recall from Wednesday's lesson that this expression, this quantity here, is actually related to the perpendicular distance of your line or plane from the origin. So it's somewhat related to a line that looks like, oh my god, a line that looks like, you know what, just something like this. Okay, and in fact, the distance, the magnitude of this line is actually expressed as negative theta naught over the norm of your weights vector, right? So I think you guys can see that because x dot theta is equal to, again, the norm of x, the norm of theta, and the cosine of the angle between them. And if you divide both sides by this, you just get the x cosine d, which is the distance, right? So that should be pretty clear. Okay, so far, any questions? Everyone understand? Okay, so everyone understand. Then we can go ahead and write an expression for general linear classifier, which is not constrained by a decision boundary that is strictly through the origin. So it will still be called H. And now it has two parameters, theta and theta naught, which again, the output is just a sign of this operation. And okay, I have to stress this again. These two are of the same dimension, whereas theta naught is strictly a real number. Okay, a scalar, it's not a vector. Okay, so with that said, before we actually move on to talk about errors and so on, there's one concept that we should understand that is called linear separability. Okay, so let's again get some data points. Let's say something like this, maybe. And for this case, you will realize that you can definitely find a solution where you can draw a linear classification boundary that is able to perfectly separate the two classes. So in the case where you can definitely find a certain linear decision boundary to perfectly classify all your data points, then we can say that this data set here is linearly separable. Okay, and a lot of the data sets will be linearly separable, so this is why linear classifiers will work. However, there are also really, really simple cases where the data set is just not separable, even though your data set has really few data points, right? So for example, one such data set will be 4 points that looks something like this. Okay, if your data point looks like this, it is no longer separable. Well, no matter how you draw the decision boundary, you will always classify something wrongly, right? And perhaps you have to use something like a non-linear line to actually draw a decision boundary that's able to separate this data set. So this is a case where your data set is no longer linearly separable, so it's just not linearly separable. And from this simple example, you'll see that a linear classifier is actually intrinsically constrained, because even though this example is so simple, it can no longer classify everything correctly. Okay, and we can actually write down a slightly more formal definition for linear separability, right? So a data set, call this Sn, and is equal to, again, the same expression, is separable only if and only if this expression is true okay. So this is a more formal definition of what is linear separability, and this little expression here is pretty important for us when we actually go ahead and declare the error. So let's go ahead and take a closer look at this. So yi is actually your label, right? So it's 1 or -1, and this expression on the right side here is actually just the output of your classifier, right? It has to be larger than 0 for all the data points in a data set for the data set to be linearly separable. And for this expression to actually be larger than 0, you realize that the sign of yi, write this, the sign of your label has to be the same as the output of your classifier, right? So they have to output the same sign. That means you're predicting the same class as the label. Okay, so it's a really simple expression which tells you that as long as your prediction is correct for all the samples, then then data samples are linearly separable. Okay, so this formula we're actually going to use to declare our error function. About error, and we'll call this E, which operates on n samples, takes output from your classifier. So actually, if you use white, so because we're operating on multiple samples, we'll again take averages. Go to n, and I'm gonna use this double bracket here. Use this. Okay. So what this double bracket mean is that if the expression in here is true, so if indeed your predicted label does not concur with the ground truth label, then it will return 1, else it will return 0, right? So we realize that all the samples which the perceptron has gotten wrong will contribute to error, whereas if you get a sign correct, then we will not contribute to the error. So you can also treat this as a form of a sort of an accuracy matrix that tells you the percentage accuracy. And we can actually express this in a more friendly manner using the equation that we have just talked about. So still double brackets, but instead of writing this does not equal to so on, we can go ahead and just write yi multiplied by the output of the classifier, smaller equal to 0. Okay, so for any case where your output of the classifier does not agree with the ground truth label, we're going to count it towards the error. Whereas if it agrees, we do not count it. So notice that we take, because of the equal sign, 0 contributes to error, meaning if your decision boundary actually intersects some data point, then those data points on the decision boundary will contribute to error. Okay, so far so good. Anyone has any question? It's really simple, right? Okay, nobody has question. I'll expect you guys to do this. Yeah?
Can I explain the yi times hx thing again? Like, what does it less than 0 means it's wrong?
Mm, 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 mm. Okay. So let's say, okay, so this expression, right? Let's say your yi is 1, and this expression is actually hxi, right? For a general decision boundary. So let's say your thing for your classifier for the ith case actually outputted a -1, then a -1 does not agree with the sign from your label, which will give you, when you multiply the two together, it will be -1. So for any cases where your sign does not agree with the ground truth label, you'll get a negative value, right? The same case for if you predict a 1 and your label is -1, it'll be negative. Whereas if both predictions agree with the ground truth, for example, 1, 1, it will be positive because it's 1. And if both output a negative, then you'll get a positive value.
So
Right?
this only like works if you only have like two classes and they're like negative of each other.
Mm-mm-mm.
Oh, okay.
So we're talking about separating data points which has two different classes. Right, so that's clear?
Yeah, yeah.
Okay. Then with the training error done, we can actually talk about how we are going to change your data such that you can classify everything correctly. And in this case, actually, is not going to involve any gradient descent, which I have previously learned. It's a simple algorithm. And let's just consider a simple case. linear classifier with a decision boundary through the origin. So we don't have to worry about that theta naught. So theta naught is equal to 0. And let's say our theta is initialized as 0. Okay. So we can write a simple pseudocode bit to illustrate this algorithm. Let's just use what, yeah. So we have a for loop first. So for every single sample in your available samples, you are going to predict, you're going to check the prediction value against the ground truth. So if your yi multiplied by xi theta is smaller or equals to 0, which means that your prediction does not match with the ground truth, and the classifier has actually made an error, then we want to do something about the weights. We want to update the weights. And you realize that this will be true as it for all the cases when classifier has just began training, because the weights are initialized 0. So for all the any kind of sample you put it into it, it will give you a 0. So the first case, we'll always have to change the weights. And how we update the weights is actually really simple. So we take theta, the new theta is actually equals to your old theta plus your current sample data point multiplied by its label. Okay, so because this is initialized as 0, then our new weights will simply be yi multiplied by xi. So let's try to understand what this bit is actually doing. Okay, so there's actually two ways to understand this. The first way is we can mathematically analyze this. So let's say we take our newly updated weights, we put it through a new sample now. Actually, the same old sample that we have just gotten wrong on. So we put this back into xi and yi. Your classifier will actually output actually. So classifiers multiplied by the ground truth will be xi multiplied by theta, right? And your theta has just been updated to that, so it's actually yi multiplied by xi and xi yi. Okay, so I just sub this expression into the theta here, and because this yi multiplied by yi here is always positive, right? Because it's the same value squared is positive. So we are actually just left with xi dot xi. And you'll recall from Wednesday's lesson that this expression should give you norm of xi squared, which will definitely be larger than 0 or larger or equal to 0. If you're in the case of xi equals to the origin, then it's going to be 0, right? So you realize that because we updated the weights to this value, then your new output from the classifier will actually output a positive value that will agree with the positive value, meaning that the sample is now classified correctly. Okay? So this is doing something useful. We can be sure of that. So that was kind of abstract because we're just looking at mathematical expressions. Here's a more, perhaps more intuitive way of seeing this. If you look at, we do some geometric analysis. So we explain this uh, geometrically. For that, I will draw the decision boundary at some point. So let's say this is x1, 2, and let's say I have some random decision boundary through the origin. That's too long. God. Okay. And maybe it has a vector that's like this. Actually, I just want to copy this. And let's say we have this so this decision boundary is actually classifying everything here negative and everything here positive. So let's have a point here that's actually positive, meaning that this is actually classifying wrongly. And it will have some vector like this, right? This is xi. So recall from the previous expression, your theta, your new theta, is actually equal to something like this, right? And in this case, because your yi is 1, right, because it's a positive sample, we'll just be concerning with xi. So your new theta is just equal to xi, and we can, with that, draw our new decision boundary after the update, which would just be something like this, right? This is your data, this is after update. And you'll see now that this decision boundary is able to classify this point correctly, right? So this side is positive, this side is negative. And we can actually make a second update just to see what it's doing. So let's say we have the same plot here. This line, this. Oh, actually, just copy this again, actually. Oh, never mind. Just redraw this. There's a point here. So this point is still positive, and your data is now like this. And let's say we have another point. Let's use blue this time. Here, that's also positive, which is still classifying wrongly. And so you can see that the vector for this point is like this. Then we'll have to make another update to the theta. So this time your theta will be the original theta, which is xi, plus let's call this xj. Xj multiplied by yj, and yj against 1, so is equals to xi plus xj, right? And vector addition, so this vector plus this vector will create a vector that's like somewhere here. All right, so this is xj again, and it will create a new vector here. So our new normal vector to the decision boundary will be something like this, right? And we can draw a new decision boundary through that. And you'll realize that this new decision boundary after the update is able to classify both points correctly. Okay, so indeed this algorithm works. It's pretty simple, but it works. So we have just covered the case where your decision boundary is one that's true to the origin. So let's talk about how we can generalize this to a classifier that does not want to constrain itself to a decision boundary that's true to the origin. So let me draw a line here to separate two. So for a general classifier, which just to recall, it takes a form that looks something like this. You have an offset. What is the sign of x dot theta plus theta naught? You can actually analyze that this operation here is essentially the same as doing this, right? This for each sample. So this will give you xi dot theta plus theta naught, right? So it's equivalent to this expression, which you realize is equivalent to the case for a classifier through the origin, because it's just one vector. Let's call this maybe something like this, dot another vector, right? So this is the exact same as a linear classifier with its decision boundary through the origin. Same case. So we can, with this understanding, write a new pseudocode for how the learning algorithm will work. 1 to n. So if your thing is wrong, this time we have the theta naught, then we want to update both of our parameters. So the data will be updated the same way. And your theta naught, then you realize that it's equivalent to the xi for theta is 1. So you only have to update it by yi. And with this, you actually know the general algorithm for doing a general linear classifier using the perceptron learning algorithm. All right. So far so good. Everyone understand? Any questions? Because if not, we'll move on to
一群一群。
yeah. Yep.
For the part about the decision boundary that pass through the origin,
Mm-hmm.
like when you update the theta equals to theta plus xi times yi, then y suddenly become xi yi in a.
Oh, are you talking about?
Or is it just means the update is xi? Yeah, this part.
Yeah. This becomes. This you're asking why this expression becomes this, right?
Yeah.
Yeah. So because this is the first training sample, so we're actually just analyzing the case for the first training sample.
Oh.
The first training sample, the weight is initialized to 0. So this is
Okay.
just so this just goes out. But in more general cases where we continue, then it would just be the old weights plus this. Yeah.
Okay. Thanks.
Any other question?
Can I ask why theta naught should be updated with yi? I don't really get the part.
Okay. We explain that again. Okay. So okay, let's just look at this expression. So it's pretty mystic, yeah. But you'll see that the general classifier is expressed as xi dot theta plus theta naught, right? And you realize that this expression can be re-expressed as two vectors dotting each other, which is xi theta. Oh, actually, it's 1 dot theta naught, right? So this is equivalent to this, which again simplifies back to some vector. Let's call it b dot some weight vector. This is equivalent to a classifier through the origin, right? This is equivalent because we don't have an offset. So now, if you look back to how we updated classifier through the origin, it was just this part, right? Theta equals to the new theta equals to the old theta plus xi multiplied by yi. But in this case, our inputs and weights are higher dimensional because we introduced these extra terms to the vector. So we actually have to update these as well. We have to update theta naught. So theta naught equals to old theta naught plus something. And it will be an equivalent expression to this expression. However, you'll realize that for xi, the equivalent of xi to theta naught is actually 1, right? So if you write maybe something like, I don't know, x1 multiplied by yi, you realize that x1 is just 1. So this is just theta naught plus yi. Right? Is that understandable?
Thank you.
Okay. Any other question? Okay, if there are no questions, then I'm just going to talk about some things you should take note of with the perceptron learning algorithm. So there are actually two different cases, which has some implications to how you should train using the perceptron learning algorithm. So I'm just going to illustrate them again with plots. So let's say I have, let's say we start off with a decision boundary that's tuned towards classifying a single point. Okay, so we have a theta here, and then there's some point here that is positive. So it started from 0 and now it's tuned to classify this point correctly. But let's say we have another point that's classified wrongly. In this case, something like this point here, and it's supposed to be classified as positive, but now it's being classified as negative. And this has a vector value that looks like this. So you'll recall that to update this data such that we can classify this point correctly, we will take the vector addition of this line plus this line. So the new decision boundary, that looks about right. Right, yeah. Has a chance of actually misclassifying this original point. Right now it's overlapping, right? Because this point is really far away. So your new decision boundary actually is, after tuning, it will only be able to classify this point correctly. Now it won't be able to classify this point correctly. So that means during the learning process, there are some times where the individual points can nudge the data to a certain direction that causes it to misclassify some certain previous samples. So you have to be careful of that. To counter this problem, you have to put your training set, the same training set, through the perceptron multiple times, such that it can learn to adjust the data such that will achieve a balance that can classify both points correctly. So that's one thing to be aware of. You have to put your samples through multiple times. Another reason why you might want to put the same training set through the perceptron learning algorithm multiple times is that there are cases where one pass might not be enough for you to correct the decision boundary to classify a previously misclassified point correctly. So let's say we have decision boundary that originally looks something like this with a really long data. Okay, and you have so this side is positive, this side is negative, and you have a point that is like somewhere here, and you want this point to be classified positively. This will be oh my god, some vector that looks like this. Okay, so you realize that if we perform the vector addition again, is this theta now plus this new theta, something like, okay, that's not tilted enough. Yeah, so this will give you a new, let's use green maybe. It will give you a new normal vector that looks something like this, which would mean that your decision boundary probably looks something like, okay, something like that is good enough, which still classifies this point wrongly. All right, so you realize that you have to pass this point multiple times such that this can be slowly tilted back such that it classifies this point correctly. So this is another reason why you want to put your same training sets, same training samples through the learning algorithm multiple times. So two things to be aware of. But you guys already put through your training samples through the learning algorithm many times already anyways. Okay, but just take note of this. So if there are no other questions, we'll move on to talk about the hinge loss and stuff like that. Everyone's okay? Okay, quiet means okay. Then I'll move on. Okay, so to talk about just now we talked about perceptron algorithm, which is a pretty naive traditional algorithm, which does not involve any gradient descent. And now we want to talk about how we can improve upon that method. So to improve upon that method, we have to first analyze some constraints of using a simple perceptron algorithm to tune our parameters. So to illustrate some constraints, I'm going to plot some data points again. Oh, actually, I don't have XCs already. No, okay. Make a new one. Okay, so x1, x2. I'm gonna have 3 data points. Actually, yeah, 3 data points. Why not? So I have 2 of this class and 1 maybe here. So this is negative, positive, positive. Okay, so one thing with the perceptron algorithm is that it finds one possible solution that can linearly separate this data set. So for example, it has no preference over a decision boundary that looks like this. Let's call this theta 1 versus a decision boundary that looks like this, right? In the perceptron's eyes, these solutions have equal merit because they both can separate the training samples correctly, right? You'll notice that both boundaries will classify all the points correctly. Okay, So for any perceptron algorithm, it can output any of the correct solutions. It does not care where the decision boundary is actually. And this is a problem because if we now introduce some test data sets or validation data sets that is sort of scattered around your existing training samples, something like this, you'll realize that data 1 is actually not able to classify all the test samples correctly, right? Because it's so close to this data point that as long as there's a little bit of noise that can offset this point, as seen from the test samples, some sample will go over the boundary, which causes it to be misclassified. Whereas this theta 2, which is considerably farther away from both of the peripheral data points, is able to classify still all the test samples correctly. So that points to a desirable property that we want for our decision boundary, which is for it to be kind of spaced out from sample training data, training samples, right? So we wanted to sort of lie in the middle between the two clusters of points. So let's talk about how we can make that happen, how we can address this. And I'm just gonna draw another plot. Copy this. So let's just sort of have a decision boundary here. Actually, let's use white. And we have some data points. And we want this decision boundary to be far away from our data points. Maybe about this far. Okay, so we can actually see this decision boundary as sort of a decision boundary with some margin, right? And we can visualize the two margins. So that's the margin on the positive side, margin on the negative side. Okay, let me draw the normal vector. Okay, so you can sort of think of this decision boundary now having two margin lines. Okay, this should be equidistant. Okay, so one on the positive side, one on the negative side, and we want to keep our data points beyond the margins. Okay, and we sort of want to find a way to express these two margins. Okay, so one thing about the margins is that they are parallel to a decision boundary. So we can actually express the margin on the positive side with a really similar expression to the decision boundary itself. So let's just write the decision boundary here. The decision boundary is x dot theta plus theta naught equals to 0. For the margin on the positive side, instead we want x dot theta plus theta naught is equals to 1. And for the margin on the negative side, we want this margin to be expressed as x dot theta plus theta naught equals to -1. Okay, so let's understand why we're using this expression. So let's just look at this, because if we can sort of understand this, we can understand this. So let's bring this up here. Try to re-express this a little bit. And if you go ahead and divide both sides by the norm, so this vector now is the unit vector of the normal vector, 1 divided by the norm of theta minus theta naught divided by the norm of theta. So you realize that if you just ignore this term here, this is essentially the same thing as your normal decision boundary, where this constant term on the right side actually indicates the perpendicular distance of your decision boundary from the origin, right? Which in this case is negative because this thing is shifted downwards, so this is actually your theta naught. So your theta naught is actually a positive value, right? And now that we add in this new term, which again is a constant, we're essentially shifting, for this particular case, we're essentially shifting the entire line here that this expression is trying to declare a little bit upwards. So there's a certain distance between this positive margin and the decision boundary that can be expressed as 1 over the norm of theta, right? So this is actually the distance between your decision boundary and your margin. And this is the same for the negative decision boundary. The absolute distance here is the same, right? Just that this is shifted negatively, so it's pushed down instead of up. Okay, so that should be pretty understandable. And with this, we realize that the expression 1 over theta, which is equals to the sort of distance between your boundary and the margin, has a free parameter which we can make use. The norm of theta. We can make use of this to control the distance between the margin and the which essentially controls how far away we want the data points to be from our decision boundary. Okay, so for a smaller theta, for smaller norm of theta, your decision boundary will actually, your margins will actually become larger. And if this term is larger, then you'll realize that your decision boundaries will be less thick, so the margins will be less. Okay, so this is one term we can control, and we can sort of manipulate this relationship to adjust how big we want our margins to be. And with this, we can actually move on to how
Okay,
we talk about.
how do you adjust it? Isn't theta something that is trying to be learned instead of like we
Yeah.
deciding?
So we'll get to how we can adjust this like right now, right? Okay.
Okay, sure.
Alright. So we have this term here, which can be roughly treated as like a form of regularization, right? Let's just say the way that we control this magnitude of data to be a form of regularization. So we still need a sort of a function that can tell us how we want to adjust data such that it can classify stuff correctly, and that will be the loss, right? So just now was the error, now will be the loss, because we're trying to make this an optimization problem. So let's declare a loss function that can help us do that, which will be pretty similar, using a really similar expression to our training error we talked about for perceptron. So the loss function, let me just call this loss, and it operates on the classifier. So fixing the ground truth multiplied by, so this is a loss function for each data point. So this is just the same expression we saw just now, and we'll declare this a little bit differently. So it's actually a conditional function. So in a case where, let's call this portion here, let's call this z, so we don't have to keep writing the same stuff. So if your z is actually larger or equal to 1, meaning that, again, this is only possible if your yi has the same sign as the output of the classifier, then we'll say that it contributes no loss, right? Because it's classified correctly. Whereas on the other hand, we'll take 1 minus whatever this term gives, right? So for the case where z is smaller than 1. So if z is smaller than 1, then you realize that whatever here will be positive. So that means it's contributing to some kind of loss. And we can write this in a more programming friendly manner. So essentially you're taking the maximum term, putting 0 and 1 minus, whichever is bigger, you'll take it. Okay. And before we move on to talk about how we can actually formulate the objective function to turn this into an optimization problem, let's just analyze how the loss behaves, right, for points on different parts of your decision boundary. Have axes, there we go. This slightly small. Okay. So we have some decision boundary here, and it has some margins. Right, we have some margins here, and if you have so okay, negative and this is positive. If you have a point that's exactly on the margin, so this positive point, which is on the positive margin, then in this case the loss will be 0, because yeah, we just say that the margin has the function 1. So 1 minus 1 will be 0. So this will contribute no loss, right? And if you are somewhere that's halfway through, halfway in between your margin and the decision boundary, so these two distances are the same, then the loss contribution by a point that lies on this line, which, okay, still positive, will actually be now half, right? Because it's halfway through, that means the expression for this line here is, so 1 minus half is half. That will contribute half loss. And if your data point lies exactly on the decision boundary, then the loss contribution by this point will be 1, right? Because on the decision boundary has the expression equals 0. So you put in this point, which is on the decision boundary, the output will be 0, and your maximum value that you can pick is 1 minus 0, which is 1. And the same pattern repeats itself for the other side. And any point that's beyond the margins will contribute no loss. Okay, so that should be able to help us understand the loss function. And with the loss function done, we can actually talk about how we can define an objective function that will help us at the same time try to get a correct decision boundary that can classify stuff correctly, while also adjusting this magnitude of the data such that we can have a regularization effect where we try to push our decision boundary as far away from the data points as possible. Okay, so objective function. Okay, so we're trying to do two different things here. We have to include the loss term and the regularization term. Let's declare this as J. And samples has parameters data and data not. Okay, so we do the averaging thing. Actually, should I use white? Let's use white. And this objective function here actually includes a loss term. So because our loss term operates on a sample by sample basis, we'll do the average of the loss here plus, okay, so this term here is outside of the loop, regularization term which controls the size of a margin, which you guys have already learned is this, right? So this is basically your L2 regularization. Okay, so you'll see that this term, as your data, the norm of data gets larger and larger, the loss contribution will be larger and larger, meaning that you would like your data to be smaller and smaller, which means that you want the decision margin to be larger. Okay, and data again is a hyperparameter that controls how strong the regularization rising effect is. Okay, so you guys should be familiar with this because we have done this previously. And just for fun, because this loss function is actually kind of unique, we can try to find the gradient of the objective function. So let's just do it with respect to data. Okay, so because this loss function is conditional, so you have to differentiate this function for the conditions that it has. So for the first case, just 0. And for the second case, it's just becomes something like this. Say z is smaller than 1. And the differentiated result, this term is just 2 lambda data. Okay, so you have a little bit of a strange derivative here. Okay, so that's the derivative function, and we can try to minimize this objective function using gradient descent that will help us draw decision boundaries that can achieve our goal, right? Just as a last thing, I want to briefly, it's not the last thing, but I want to briefly touch on a little bit about how the lambda actually affects your entire model. let's call this effects of lambda. Okay, so let's start with a small lambda. That means your regularizing effect is not very strong, so it doesn't really try that much to make the margin very big. Decision boundary. The margin will be kind of close to your decision boundary. And for a case like this, we can actually observe that the points that makes the biggest impact on how your decision boundary is oriented are actually these points that's near the margin, right? So just these points contribute a lot to how the decision boundary is oriented. Whereas if we increase, if we go ahead and increase lambda is large. Try to get the same data points. So same set of data points. So now your margin is quite large, meaning that it might compromise the ability of your decision boundary to classify everything correctly and instead ignore some points near the boundary. So it might result in something that looks like this. This is your margin. It will allow some data points to go into the margin. And you realize that this orientation of your decision boundary is actually affected by more of the points, right? So these points actually now affect how the decision boundary is oriented. And that is just an effect of the lambda. So you have a really large lambda, then you're taking points that's more into the cluster of your data points to orientate your decision boundary. Whereas if a lambda is quite small, then the data points near the edge of the clusters will have a larger effect on how the decision boundary is oriented. And this is for the same set of data points. Okay, so any questions so far? We've talked for about an hour now.
Sorry, could you explain the adjustment process of that decision boundary again? I didn't fully get it.
The lambda?
Not just the lambda, like the how the decision boundary is adjusted, essentially.
What do you mean by that? The loss? You mean the loss?
Like the orientation, how the orientation is found.
Okay.
One with the vector addition.
So for small lambda, right? So you're talking about, I'm guessing these two examples, right?
Oh, no, the part way before.
This?
Crap, actually even before that.
So you're talking about this now?
I think so, yeah.
How the lambda changes the margins, is it? Is that what you want to know more about?
Dang, it's actually the part before even the margins. Yeah, that one.
I deleted it. That's interesting. Okay, so you're talking about a perceptron learning algorithm.
Yeah.
Okay. Let's just go through that part again then. Let's see. Where do we talk about again? Oh yeah, let me just write the pseudocode. How about that? So for a set of samples, then okay, this expression you know, right? Okay, let's just do the simple case where this thing is actually smaller or equal to 0. Then this means that this your classifier has outputted the wrong label. Then you want to adjust the theta somehow, right? So the adjustment for theta is given by theta plus xi dot yi. So I'm guessing you're not clear about this part.
Theta is like, does it describe the vector representing the boundary?
So theta is actually this normal vector here.
Oh, right.
Right. Okay, so I guess you're not familiar, not fully understanding what this operation is doing.
What is XIYI?
Okay, so xi is your data point for one particular case. So you can, it's just the coordinates of the points, right? So maybe 1 or 2 or something like that. Right, that means if you have a plane, so I just write x1. So it will be 1 and 2, right? So this is where your data point is. Okay, and yi is the class of this data point. So it's either 1 or -1. So let's say this is 1. So then you have, so let's say this is a positive class, so that means it has the value of +1. Then you would just multiply these two together to give you the and add on to the old weights to give you new weights. Okay, so far okay, right? You understand what xi and yi is, right?
YI is the class. XI is like
The
the
data point,
yes.
the location of the data point. Okay,
Yeah.
so okay, now this is a really mystic expression, so let's understand intuitively what it's doing, right? So we have, let's just do the geometric analysis. So if we go ahead and have, let's say, a point that is somewhere here and supposed to be classified positively, and now you're classifying this wrongly, right? Say, let's say your decision boundary is something like this. Actually, we don't even need to draw a decision boundary. Let's just say our decision boundary is 0, so we have no decision boundary. We're at the start of our training. Then what this operation is doing is essentially taking, because currently our decision boundary is 0 plus xi, which is this vector here that points to the current data point, multiplied by its class, which we know is 1 plus xi. All right, so the new decision boundary that we will create after the adjustment is just xi, which will look something like this, right? The normal vector would just be xi. And you realize that this decision boundary after adjustment is able to classify this point, which previously is classified wrongly, now correctly. And if we go ahead and put in even more points, for example, we have a point here that's also classified wrongly, then our new theta will be the old theta, which is xi, plus, let's say this is xj, right, plus xj and yj again is positive 1, so equals to xi plus xj. And vector addition, you should know, essentially we're taking this vector and then we add on the direction of this vector, which is like that, creating a new normal to the decision boundary, which is now able to classify both points correctly, right? So both points are on the positive side. And that is basically what the perceptron learning algorithm is doing.
Could you illustrate what happens when the class is like negative?
Okay. So let's see. Let me just this. Okay. And now erase this. Okay. So let's say your class is negative and it's here, which is classified wrongly, right? And again, we call this sample xj or something. Let me just. Okay, that's fine. So this is xj. This is the vector that points to this point, and it's -1. So your new theta is xi plus xj yj, which yj in this case is negative, so xi minus xj. Okay, and xi minus xj, pretty sure Alistair would have talked about this during Wednesday's lesson. It's basically like here, like a vector that's between these two, right? You're taking from yeah, basically that's what the deduction is doing. And you can shift this new vector down here to the origin, and you draw a new plane that's normal to the normal vector. Okay, this is really bad drawing, but and you'll see that this is actually classifying both things correctly.
That's cool. Thanks.
Yeah. Okay, so everyone's good.
Yiqing, I want to ask about the loss function
Okay.
part.
Mm-hmm.
I want to ask, right, like why the threshold suddenly become 1 and like greater than 1 or smaller than 1 in the loss function, whereas before it's like greater than 0 or less than 0. Because apparently like yi is still 1 or negative 1.
Mm-hmm.
And then the theta xi plus theta 0. Like, I mean, I just don't get why this c suddenly become like, if it's greater than 1 is 0, is smaller than 1 is 1 minus z.
Okay. So first, let's analyze this term, right? So you're right that this term is still limited to negative 1 or 1. Okay, so it's either of these. But for this term here, it can be stuff of any value, right? It can be any value. It can be 0, it can be 1, it can be negative 2, so on. Because if your point is really far away from the decision boundary, which in this case, this looks like about a 2, right? The output of the classifier will actually not output this as +1 or -1, it will be 2, which is still positive, meaning that it's classified correctly. So that means the whole expression here can take on any real value. Okay, so now that's okay. If the case where your z, which is the yi multiplied by the classifier, is going to be larger than 1, that means the output of the classifier is actually corresponds to the label, right? So that means it's a correct answer. Therefore, we do not want it to contribute any loss. Okay, and maybe I should make it clearer by saying that the classifier is actually defined slightly differently now. Whereas in the old one, I just use x. You're actually just taking the sign of the thing. This new classifier in the case of trying to apply hinge loss is actually just the output of the operation. So we're not taking any signs. Okay, so it can be any value. And again, if it's smaller than 1, this means that if you recall, the margin here is actually declared as 1. The only way for z to be smaller than 1 is that your points are inside the margin, right? Inside the margin, somewhere in this space, which will now contribute to the loss because we do not want points within the margin. Does that make sense?
But isn't you may already have the assumption that all these predictions are correct? But if they are correct, then why at the first place there's loss?
We're not assuming anything about the data points because this function can output negative and positive values, right? Because this operation here does not necessarily need to be classified correctly. So this can be
even if it's classified correctly, but if fall between the margin and between margin and boundary, it still contribute to a loss because
so if it's anywhere in this space, it's going to be contributing to the loss because we want the data points to be outside of the margins.
All right, thanks.
Okay, any other questions? What happened to Billy? Should we wait for him? Okay, actually, I'll just have one last thing to cover before they can go do the thing. Which is not that critical, I guess. Not that critical. So that one last thing is actually about validation dataset. Which is helping us tune our hyperparameters. Okay, so what I mean by hyperparameter, one very obvious one is your lambda, which controls the regularization effect, right? So I want to do a plot for how the loss function will look like as you adjust lambda. Okay, it will actually look like some exponentially decreasing curve for your normal training loss. Okay, and if you try to do this like manually, you try to plot, you try to do training losses, and then you try to average them and make a plot yourself, and while adjusting lambda, you'll get a trend curve that looks something like this. So this is empirically verified. However, when we're training machine learning models, we're not so concerned about training loss. We're actually more interested in how accurate the model can be generalized to the test set. Okay, but for a test set, we obviously can't obtain the losses because you don't have access to the test set. So, but we can still sort of plot a test set loss, like a make-believe test set loss curve. That will look something like this. Okay, so we have some minima here, and on the right side here, this is the test. If you try to somehow plot a loss curve for the test set, it'll look something like this. So on the right side here is actually overfitting. On the left side here is underfitting. And you want to select the lambda, the hyperparameter that's resulting in the least loss. Okay, that makes sense, right? You want to have it as accurate as possible. So you want to select a lambda that's here. And because we do not have access to the test set, we cannot actually plot this curve. We do not know this curve. So instead, what we do is we take a small portion. Let's say our training set is like this. This big box is your training set. And you have maybe some test set that's outside of the training set, which you do not really have access to calculate loss. So instead, to mimic the effect of being able to calculate the loss for this test set, you take a small portion of your training set, which is called a validation set, and you evaluate the model's loss on this validation set for every single epoch. Then you can sort of obtain a curve that closely approximates the loss curve for a test set. And by looking at the validation loss, then we are able to tune our hyperparameter to see which parameter will allow us to generalize our model better. Okay, so this is like a trial and error process with the validation data set. And how you take this validation set, usually you're going to have about 3/4 of it to be training and 1/4 of it to be validation, and the rest test set. So if you have access to an entire set of data that's not separate in training, test, and validation, then a common ratio to use is training is 60%, your validation is 60%, oh no, 20%, and your test is 20%. Okay, so this is some common splits. You can search it online. But if you're just working with training set, you want to split into validation, 1/4 to 3/4 is okay. Okay, so using the validation set will allow us to sort of select hyperparameters that can make the model perform slightly better. So I think this should be a pretty simple idea. And a lot of you guys are actually already using some validation things, validation-like things in your previous assignment. So I think that should be fine. Okay, so actually I have nothing more to talk about. So does anyone have any questions? Because if you do not have a question, you yeah.
Okay, could you explain again why the margin is like the right side of the margin is 1
Oh,
and minus
okay.
1?
Let's just draw. Okay, let's just do it here, I guess. No, not this. Okay, draw in the center. So let's say I have some margin like here. So your concern is which side is positive and which side is negative, right?
My concern is why is it 1 in the first place?
Why is it 1 in the first place? You mean the margin? Oh, the margin, right?
Yeah.
Oh, okay. So actually 1 is just some randomly defined attribute. It can be 2, it can be 3, but we just use 1. Because this property here is not really that important in controlling anything. because the really important parameter in controlling how wide your margins are is actually the norm of data. So this thing here is kind of arbitrary. We just chose 1 because one, everybody likes 1. So
Okay, sure.
yeah. If there are no other questions, there is a new assignment in the Google Drive called linear classification. You can go ahead and read it and do it now. You guys have 14 minutes to start work on it. Of course, you can, if you have any question, just stay online and ask.